Today our subject is nervous regulation of circulation and rapid control of arterial pressure. Arterial pressure is very important, you know. Normal arterial pressure varies between 120 and 80 millimeter mercury. 120 millimeter mercury systolic and 80 millimeter mercury diastolic. It can vary during the day. In the morning it is a little bit low. During daytime, when you are physically active, mentally active, then it will increase. Your blood pressure will increase. And when you sleep, it will go down again. It will be the lowest value. How is it regulated? Blood pressure is regulated by both ways, by nervous system and by our kidneys. Today we are going to talk about the nervous regulation of blood pressure. Tomorrow we will learn about how blood pressure is regulated by the kidneys. Kidneys regulate the blood volume, extracellular volume, and the sodium concentration in the extracellular fluid. It is very important. It is a long-term regulation of blood pressure. Okay, kidney function is important in the long-term regulation of blood pressure, whereas nervous system is important for the short-term regulation of blood pressure. Again, I should say that this presentation is prepared from shorter version of Guyton. I recommend you, if you have time, to read the normal long version of Guyton to better understand the subject, especially if you cannot understand some part, a part in the lecture. You can go to the text, okay, and read and understand. Okay, after listening to this lecture, you will be able to describe the effects of sympathetic stimulation on blood vessels and heart. Generally, sympathetic nervous system constricts, narrows the blood vessels and increases the heart rate and contractibility. And you will be able to describe the effects of parasympathetic stimulation on the cardiac function. Its effect is just opposite, okay, slows down the heart. And you will be able to define how the vasomotor centers of the brain control the sympathetic vasoconstrictor system. In our brain, in the medulla oblongata, upper part of it, and upper part of spinal cord, and pons, lower part of the pons, the brain stem. There are vasomotor centers located there, and then they control the sympathetic vasoconstrictor system. Higher nervous systems also regulate the functions of the vasomotor systems, vasoconstricting, vasodilating, cardio-accelerating centers are located here, and they are affected by the cerebral cortex, different parts of the cerebral cortex. You will be able to define the effect of sympathetic stimulation on the adrenal medulla. Adrenal gland is connected to the sympathetic nervous system. It behaves as if a ganglia of the sympathetic nervous system. So when we are alert, we are excited, adrenal medulla will be also stimulated and will release epinephrine and norepinephrine into the blood circulation. And you will be able to define the role of nervous system in rapid control of arterial pressure. What does this mean, rapid control? Let's say when you are sleeping in the lying position, okay, when you stand up, due to gravity, blood pressure in your brain, in your upper extremity, will suddenly go down because the blood will go downwards. So blood pressure goes down and your brain may not receive enough blood when you stand up. So you may feel dizzy, you may faint, but due to this rapid control of arterial pressure, sympathetic activity will suddenly increase, and then your blood vessels will constrict and your heart will beat faster and stronger, so that will provide enough blood to your brain, so you will not fall down, you will not faint, okay? And then you will be able to explain the role of autonomic nervous system in blood pressure regulation during exercise. When we do exercise, our blood in our body should be redistributed, okay? And normally the blood is distributed equally to all our body organs and the muscles. However, during exercise, our internal organ circulation should go down, and whereas our skeletal muscles should get much of the cardiac output, so it is arranged, it is adjusted by autonomic nervous system, okay? Generally sympathetic activity will be increased during exercise, and then the blood vessels going to our viscera, our internal organs, will be constricted, and the blood vessels going to the skeletal muscles, to the heart, will be dilated. So we are going to learn about them. And then you will be able to describe how the arterial baroreceptor reflex work to control blood pressure. Shortly, we have baroreceptors located in carotid bodies and arcus aorta, sensing, detecting the blood pressure all the time. When blood pressure goes up, they start to fire faster, and then they inform the brainstem, okay? And then sympathetic activity will go down, and then blood pressure will go down by vasodilation, by decreasing the heart function, decreasing the rate and also contractility of the heart, so that the blood pressure will go down. The opposite is also true. When blood pressure goes down, then firing will be less frequent, and this time sympathetic activity will not be inhibited, okay? So the blood vessels will constrict, and the heart will start to beat faster and stronger to increase the blood pressure. You will be able to explain how baroreceptors maintain arterial pressure relatively constant during daily changes in body posture. I have just mentioned to you about earlier, about getting up when you are in a lying position. Blood pressure can go down. You will be able to define the importance of baroreceptors in the long-term regulation of arterial pressure. I should say unimportance actually here, okay? Because in the long-term regulation of blood pressure, our baroreceptors are not good. So they adapt to the new point. Let's say your blood pressure is 120 systolic, and then your baroreceptors are set to 120 millimeter mercury. If it increases further, let's say 140, 160 millimeter mercury, baroreceptors starts to fire. When your blood pressure stays high, let's say 160 all the time, your baroreceptors will stop sending frequent firing to the brainstem, okay? They will adapt to the new point. That's why they are not good in the long-term regulation of arterial pressure, okay? And we are going to learn about how cardiopulmonary reflexes help to regulate arterial pressure. Yeah, here we have we have a low volume sensing stretch receptors in atria and the ventricles. If the blood volume goes up, it inhibits it stimulates the heart to pump blood further. Okay, we are going to learn about them, and then you will be able to answer the question that whether the carotid and aortic chemoreceptors take part in the arterial pressure regulation. You know, there are baroreceptors in the same location in carotid body and aortic arcus aorta. There are also chemoreceptors there. Chemoreceptors are sensitive to to blood oxygen level, blood carbon dioxide level, and hydrogen. Okay. These receptors are also sensitive to pressure changes. It's interesting, but they are sensitive to low blood pressure. Okay. Baroreceptors are sensitive to high blood pressure, and you will be able to define the central nervous system ischemic response to decreased blood flow to the brain. The brain is selfish, I should say. When your blood pressure goes down for any reason, especially due to hypovolemia, due to bleeding, okay, the brain sends signals to all other parts of the body, constrict the blood vessels except the brain. Okay, so blood pressure goes up to 200 millimeter mercury or so, to very high values. All right, and all other organs, blood vessels are constricted, and then blood is directed to the brain itself. This is called ischemic response, central nerve of the nervous system. It is a sign that the patient is going to die soon, especially when the patient is in shock. Okay. And finally, we will see the Cushing reaction of the central nervous system. Similarly, central nervous system has cerebrospinal fluid circulating. Okay, it is synthesized inside of the ventricles in the brain, and it is circulating, going out of the brain to subarachnoidal space, and then it is sucked to the venous system. Okay, it is synthesized all the time and returning to the subarachnoidal veins to the general circulation. Sometimes this cerebrospinal fluid amount can increase and can press on the brain. You know, the brain is located inside of the skull. Our cranium is made of bones, and the volume of the cranium cannot be increased. Somehow, if the pressure inside in the cranial vault, then the pressure will be stimulated to be increased, so that to provide blood to the brain. It's okay. So we are going to learn these subjects. Let's start. Except for certain tissues such as skin, blood flow regulation is mainly a function of local control mechanisms. Okay, we have learned about them. The amount of oxygen in the tissue can go down, carbon dioxide level, lactic acid, hydrogen concentration, they can go up. So these cause vasodilation in the tissue. Nervous control, on the other hand, mainly affects more global functions, such as redistributing blood flow to various parts of the body, increasing the pumping activity of the heart, and providing rapid control of arterial pressure. This control of circulation by nervous system is made possible by using autonomic nervous system section of the nervous system. Okay, nervous system is consisted of central nervous system and the peripheral nervous system. This autonomic nervous system is a part of the peripheral nervous system. Autonomic nervous system has two sections, sympathetic and parasympathetic nervous systems. Okay, sympathetic nervous system is important for controlling the circulatory part of the circulation system, blood vessel part, I may say, also heart, including the blood vessels. On the other hand, parasympathetic nervous system has effects on the heart mainly, not much effect on blood vessels. So sympathetic stimulation causes vasoconstriction and increases heart rate and cardiac contractility. Sympathetic vasomotor fibers exist the spinal cord through all of the thoracic and first one or two lumbar spinal nerves. So there are sympathetic chains on both sides of the spinal cord. Let's see the picture. Oh, sorry, it's not here. It's quite. Okay, you see here sympathetic chain located on both sides of the spinal cord. Just a second. All right, now you see on both sides. This is truncus sympathicus. Okay, in this figure we also see the nervus vagus. This is parasympathetic and inhibiting cardiac functions. The others are all stimulating. Okay, vasomotor centers are also seen in this graph, in this figure. Let's go back. Where were we? All right. Okay. So these sympathetic nerves, they go to blood vessels of internal organs, to the skeletal muscles and the heart altogether. All blood vessels are innervated by sympathetic nerves except capillaries. Okay, let's see. Here you see this is the sympathetic nerve innervating the vasculature. This is microcirculatory area, we can say. This part is a microcirculatory area. This is arteries and veins. As you see, the sympathetic nerves innervate arteries, veins, and also arterioles. Okay, so these blood vessels receive sympathetic innervation, so they are constricted, narrowed due to sympathetic stimulation. But capillaries, they don't have sympathetic stimulation. Capillaries, they don't have a smooth muscle, okay? You know it. They are single cell endothelial, made of endothelial cells. So in this way, their wall is made of single cell, endothelial cell. So they allow diffusion or transport of substances between interstitial tissue and the blood. All right, sympathetic fibers also go to the heart and stimulate its activity, both increasing the rate, heartbeat, how many times the heart contracts in a minute, and strength of pumping. All right. Now, parasympathetic stimulation. Parasympathetic stimulation decreases the heart rate and cardiac contractility, although the parasympathetic system plays an important role in controlling many other autonomic functions of the body. Its main role is in controlling the circulation is to decrease the heart rate markedly and slightly decrease the heart muscle contractility. Okay. Control of sympathetic vasoconstrictor system by the central nervous system. Sympathetic nerves carry large numbers of vasoconstrictor nerve fibers and only a few vasodilator fibers. Vasoconstrictor fibers are distributed to almost all segments of blood circulation. Their distribution is greater in some tissues such as skin, gut, meaning gastrointestinal system, and the spleen. Vasomotor centers of the brain control the sympathetic vasoconstrictor system located bilaterally in the reticular substance of the medulla, and the lower third part of the pons is an area called vasomotor center. Let's see, in this figure you see vasomotor center, and then here closer look at the vasomotor centers, which transmit sympathetic impulses through the vagus nerves to the heart and sympathetic impulses through the spinal cord and peripheral sympathetic nerves to almost all blood vessels of the body. Okay, so as I said, truncus sympathicus on both sides, sympathetic nerves innervate to all blood vessels and the heart. Okay. Although the organization of the vasomotor centers is not completely understood, certain areas appear to be especially important. A vasoconstrictor area is located bilaterally in the anterolateral portions of the upper medulla. The neurons originating in this area secrete norepinephrine, and their fibers are distributed throughout the spinal cord, where they excite vasoconstrictor neurons of the sympathetic nervous system. A vasodilator area is located again bilaterally in the anterolateral portions of the lower half of the medulla. The fibers from these neurons inhibit vasoconstrictor activity of C1 area, so that causes vasodilation. Here, this picture shows the effects of higher centers on vasomotor center in the pons and medulla oblongata. These lines, continuous lines, are vasoconstrictive. Dashed lines are vasodilating effect they have. You see that upper centers also they affect the vasomotor center. We will tell later, but I can say to you that motor stimuli, for example, when you are exercising, your motor cortex will send signals to alpha motor neurons in the spinal cord to stimulate the skeletal muscles. At the same time, from the motor cortex, there will be parallel stimulation to the brain stem to accelerate heart and to constrict the blood vessels in internal organs, I mean to increase sympathetic activity, to provide blood during exercise to the skeletal muscles. Okay, I can say motor cortex can also send signals to the respiratory center. Respiratory center is also located in the medulla. And a sensory area is located bilaterally in the nucleus tractus solitarius in the posterolateral portion of the medulla and lower pons. The neurons of this area receive sensory nerve signals mainly through the nervus vagus and the nervus glossopharyngicus, and output signals from this sensory area help to control the activities of vasoconstrictor and vasodilator areas, providing reflex control of many circulatory functions. An example of this is baroreceptor reflex, controlling arterial pressure. Continuous sympathetic vasoconstrictor tone causes partial constriction of most blood vessels. Normally, vasoconstrictor area of the vasomotor center transmits signals continuously to the sympathetic vasoconstrictor nerve fibers over the entire body, causing slow firing of these fibers at a rate of about 1 impulse per second. This sympathetic vasoconstrictor tone maintains a partial state of contraction of the blood vessels. When this tone is blocked, for example, by spinal anesthesia, the blood vessels throughout the body dilate and arterial pressure may fall from 100 to 50 millimeter mercury or so. So this is the experiment. Now we follow the arterial pressure, let's say in a dog, and then we apply spinal anesthesia to this animal, and then we see that the blood pressure, arterial pressure goes down suddenly, okay? And if we inject the neurotransmitter of the sympathetic nervous system, for example, norepinephrine, we see that it increases the blood pressure temporarily, because the norepinephrine we injected will be metabolized and will be removed from the blood, okay? So this experiment shows us the importance of continuous sympathetic stimulation on blood vessels, so that sympathetic tonus is very important to keep blood pressure high, okay? Vasomotor system is influenced by higher nervous centers. Large numbers of areas throughout the reticular substance of the pons, mesencephalon and diencephalon can either excite or inhibit the vasomotor center. The hypothalamus plays a special role in controlling the vasoconstrictor system and can exert powerful excitatory and inhibitory effects on the vasomotor center. You know, the hypothalamus it controls the vegetative functions of the body, body temperature, blood pressure, how much water you are going to drink. I mean, are you going to feel thirsty or not? So it follows the osmolarity of our blood, okay? Whether you are going to eat or not, we have their satiety centers also, very important part of the brain, our hypothalamus. And many other parts of the cerebral cortex can also excite or inhibit the vasomotor center. For example, stimulation of the motor cortex excites the vasomotor center. Many areas of the brain can have profound effects on cardiovascular function. All right, as I said earlier to you, we have seen this picture. Now we see it again. This part is located the hypothalamus, okay? There is thalamus somewhere here, and just below it there is hypothalamus. Thalamus is a place eliminating unnecessary income, sensory stimulations, which ones are going to be transmitted to the brain or not, it decides. And hypothalamus controls the vegetative functions of our body. Norepinephrine is the sympathetic vasoconstrictive neurotransmitter. You know, other transmitter of sympathetic nervous system is epinephrine. Norepinephrine, which is secreted at the endings of the vasoconstrictor nerves, acts directly on alpha adrenergic receptors of the vascular smooth muscle to cause vasoconstriction. Okay, we have alpha and beta receptors in the tissues, in the blood vessels in different tissues. Accordingly, sometimes we see vasoconstriction, sometimes vasodilation. For example, the adrenal medulla. Adrenal medulla releases norepinephrine and epinephrine during sympathetic stimulation. As I said earlier, adrenal medulla behaves as if a peripheral ganglion of the sympathetic nervous system. So sympathetic impulses are usually transmitted to the adrenal medulla at the same time. They are transmitted to the blood vessels, stimulating release of epinephrine and norepinephrine into the blood circulation. These two hormones are carried in the bloodstream to all parts of our body, where they act directly on blood vessels to cause vasoconstriction through stimulation of alpha adrenergic receptors. We have just seen the effect of norepinephrine. Now epinephrine. Epinephrine, however, also has potent beta adrenergic effects, which cause vasodilation in certain tissues, such as skeletal muscle and also in the heart, in coronary arteries. Role of nervous system in rapid control of arterial pressure. One of the most important functions of the sympathetic nervous system is to provide rapid control of arterial pressure by causing vasoconstriction and stimulation of the heart. At the same time, sympathetic activity is increased. There is often reciprocal inhibition of the parasympathetic vagal signals going to the heart and also contribute to higher heart rate. We can think that there is a brake and a gas pedal in the body, okay? And you want to go faster, you press on the gas pedal, and then the car starts to go faster. But at the same time, if you press the brake, it is difficult to go faster. But if you take your leg away from the brake, then your car will suddenly start to go faster. So parasympathetic activity is like a brake of the heart, and sympathetic activity is the gas pedals. Okay, if you take away the brake pedal, then the heart starts to beat faster. If you press on the gas pedal, if you increase the sympathetic activity, then the heart will beat much faster. Okay, much stronger and much faster. Okay, as a consequence, three major changes take place to the increased arterial pressure through stimulation of the autonomic nervous system. Most arterioles throughout the body are constricted, causing increased total peripheral vascular resistance and raising the blood pressure. The veins and larger vessels of the circulation are constricted, displacing blood from the peripheral vessels toward the heart and causing the heart to pump with greater force, which also helps to raise arterial pressure. The heart is directly stimulated by the autonomic nervous system, so this further enhances the cardiac pumping ability. Much of this is caused by an increased heart rate, sometimes to as much as 3 times of normal. In addition, sympathetic stimulation directly increases the contractile force of the heart muscle, so that increasing its ability to pump larger volumes of blood. Our heart is able to pump that it receives, okay? When venous return to the heart increases, for example, during exercise, the heart is able to pump as much as the blood it receives from the periphery within physiological limits. this is called Frank-Starling law. Okay, Frank-Starling law. As I said, don't forget the physiological limits is the key. Within physiological limits, it stretches the ventricles, the excess volume, and then causes a stronger contraction of the heart. An important characteristic of nervous control is that it is rapid. It begins within seconds. Conversely, sudden inhibition of the nervous system can also decrease the arterial pressure within seconds. So it is very quick. When you wake up, blood pressure goes down and suddenly sympathetic activity increases, and then blood pressure does not fall, so the person is healthy, walking, talking, or vice versa. If it is inhibited, then blood pressure suddenly goes down, and the patient blood pressure will go down, and he or she can have dizziness or faint, lose consciousness. Okay. The autonomic nervous system contributes to increased arterial pressure during muscle exercise. During heavy exercise, muscles require greatly increased blood flow. Part of this increase results from local vasodilation, but additional increase in flow results from simultaneous elevation of arterial pressure during exercise. During heavy exercise, arterial pressure can increase by 30 to 40%. Okay, so it is interesting. During heavy exercise, our muscles, skeletal muscles, blood vessels are dilated, and still we have high blood pressure because our heart starts to beat faster and stronger, and then cardiac output increases much also. That's why and the blood is redistributed. Okay, when the blood vessels in the skeletal muscles are dilated, on the other hand, the blood vessels going to internal organs are constricted. So the rise in arterial pressure during exercise is believed to result mainly from the following effect. At the same time, the motor areas of the nervous system become activated to cause exercise, to stimulate the muscles. Most of the reticular activating system in the brain is also activated by parallel fibers coming to this area from the motor cortex, which greatly increases stimulation of the vasoconstrictor and cardioaccelerator areas of the vasomotor center. These effects increase the arterial pressure instantly to keep pace with increased muscle activity. Vasodilation of the muscle, however, is maintained despite increased sympathetic activity because of the overriding effect of local control mechanisms in the muscle. What does this mean? So sympathetic activity tries to constrict the blood vessels in the skeletal muscles, but skeletal muscles are metabolically active, contracting, relaxing, so using oxygen and producing much carbon dioxide, hydrogen, lactic acid, and then these local control mechanisms causes vasodilation in the skeletal muscles. It means autonomic nervous system increases arterial pressure during alarm reaction. When you are frightened, okay, when you are afraid of something, your blood pressure can suddenly increase to very high values, such as 200 millimeter mercury within seconds. So this alarm reaction provides necessary increase in arterial pressure that can immediately supply blood to any of the muscles of the body that might need to respond instantly to flee, to escape from the perceived danger. Okay, I can give an example to you. For example, you are going home late at night, and then in your street, close to your door, there may be a dog. Okay, dog is going to bite you, or you see that, and then huge dog. a big dog, then you are afraid of, okay, what are you going to do? You can escape or you have to fight with the dog. And this is called fight or flight reaction. Okay, fight or flight reaction. In this case, sympathetic nervous system is active the most. Okay, to overcome this situation. Okay, reflex mechanisms help to maintain normal arterial pressure. Aside from special circumstances such as stress and exercise, autonomic nervous system operates to maintain the arterial pressure at or near its normal level through negative feedback reflex mechanisms. Now, arterial baroreceptor reflex control system. Arterial baroreceptor reflex is started by stretch receptors. These stretch receptors are called baroreceptors, and these baroreceptors are located in the walls of large systemic arteries and especially in the walls of carotid sinus and aortic arch. Signals from the carotid sinus receptors are transmitted via Hering's nerve, in the glossopharyngeal nerve later on, and then arrives to the nucleus tractus solitarius in the medullary area of the brain. Okay, see here. This is carotid bodies, and then Hering nerve enters the glossopharyngeal nerve, and then inside of the glossopharyngeal nerve arrives in the brainstem. On the other hand, signals coming from the aortic arch or arcus aorta, they travel inside of the vagus nerve and arrive in the medulla. Okay. Response of the baroreceptors to arterial pressure. Figure shows the effect of different arterial pressure levels on the rate of impulse transmission in a Hering's carotid sinus nerve. Let's see the figure. Okay, you see here. In the x-axis, you see the blood pressure, and y-axis, the number of stimuli going to the brain. As you see from the carotid body, we don't see any stimulus, any sensitivity below 50 or 60 millimeter mercury. However, after that, baroreceptors starts to be fired, and then between 80 or 70 and 160, they are very sensitive to the changes in the blood pressure. Okay. Aortic baroreceptors are sensitive to a little bit lower values, okay, of blood pressure. How much? 30 millimeter mercury. Carotid bodies are sensitive until 50 millimeter mercury, whereas carotid bodies are aortic bodies, baroreceptors are sensitive to lower blood pressure values. Okay. So baroreceptors control arterial pressure as follows. Increased pressure in blood vessels containing baroreceptors causes increased impulse firing. Baroreceptor signals enter the nucleus tractus solitarius in the medulla oblongata and pons, and inhibits a vasoconstrictor center of the medulla and excite the vagal center. The net effects are inhibition of sympathetic activity and stimulation of parasympathetic activity. This will cause vasodilation of the veins and arterioles and decreases the heart rate and strength, the contractility of the heart. Vasodilation of veins and arterioles and decreased heart rate and strength of the heart contraction cause the arterial pressure to decrease because of a decline in peripheral vascular resistance and cardiac output. Again, figure 18.7 shows a typical reflex change in arterial pressure caused by occluding, closing, blocking the two common carotid arteries. Let's see the figure first. Here you see this is the carotid arteries. Both common arteries, carotid arteries, are clamped here in this point. As you see, once you clamp the carotid bodies, blood pressure suddenly goes up, okay? And it stays high when clamp is there. Once you remove the clamp, you release the clamp, then blood pressure goes down suddenly. So what is the reason of this? Let's go back and then see. This occlusion, closure of the carotid arteries reduces the carotid sinus pressure. As a result, signals from the baroreceptors decrease and cause less inhibitory effect on vasomotor center. The vasomotor center then becomes much more active than usual, causing the aortic arterial pressure to rise and remain elevated during 10 minutes that the carotids are occluded. Removal of the occlusion allows the pressure in the carotid sinuses to rise, and carotid sinus reflex now causes the aortic pressure to fall immediately to slightly below normal as a momentary overcompensation and then return to normal in another minute. Okay, when you remove the clamp, this time it can go further down and then become normalized again. Right. Now, baroreceptors maintain arterial pressure at a relatively constant level during changes in body posture and other daily activities. When a person stands up after lying down, the arterial pressure in the head and upper parts of the body tends to fall. The reduction in pressure decreases the signals sent from the baroreceptors to the vasomotor centers, eliciting a strong sympathetic discharge that minimizes the reduction in arterial pressure. Okay, it causes vasoconstriction, it increases the cardiac activity so that it does not let the arterial pressure to go down. In the absence of functional baroreceptors, however, marked reductions in arterial pressure can decrease the cerebral blood flow to such a low level that consciousness is lost. We call this in our daily medical practice as orthostatic hypotension. Okay, orthostatic hypotension. When the patient is lying and then when he or she goes to the standing position, then he or she can feel dizziness. So this is called orthostatic hypotension because not sufficient. The brain cannot receive enough blood if baroreceptors do not work. Okay, if they work, they suddenly cause vasoconstriction and increases the cardiac function, heart rate and contractibility, so that normalizes the blood pressure, and then the person does not feel anything. Everything is normal. Daily activities that tend to increase blood pressure, such as eating food, excitement, defecation, and so on and so forth, can cause extreme increases in blood pressure in the absence of normal baroreceptor reflexes. A primary purpose of the arterial baroreceptor system is to reduce the daily variation in arterial pressure to about 1/2 to 1/3 of the pressure that would occur if the baroreceptor system were not present. Figure 18.8 shows the importance of this buffer function of the baroreceptors. The upper record in this figure shows an arterial pressure recording for 2 hours from a normal dog, and Lower record shows an arterial pressure recording from a dog whose baroreceptor nerves from both the carotid sinuses and aorta had been removed. So here on the upper figure, you see the baroreceptors are intact, and in the picture below, in the graph below, both carotid and aortic baroreceptors are denervated. You see the magnitude of fluctuations. The fluctuations of the magnitude are quite larger in the baroreceptors denervated. Okay, so the extreme variability of pressure in the denervated dog caused by simple events of the day, such as lying down, standing, excitement, eating, defecation, and hearing noise. Okay, they all cause extreme variability of the pressure, increases in the fluctuations, increased magnitude of the fluctuations if the baroreceptors are denervated. Okay, again another figure. I'm sure you like figures. I also do. Let's look at the figure first. Here is the figure. What do we see in this figure? If baroreceptors are intact, our blood pressure varies with a narrow range. Okay. If you cut the baroreceptors, denervate the baroreceptors, if you cut the nerves going to the baroreceptors, and then you see very wide range of blood pressure. Okay, so very important. The baroreceptor function does not let the blood pressure to go too low or to go too up values. Okay, this shows us this. Let's see. Let's look what is written here. Note that when the baroreceptors were functioning normally, the mean arterial pressure remained throughout the day within a narrow range between 85 and 115 millimeter mercury indeed, during most of the day at almost exactly 100 millimeter mercury. In contrast, after denervation of the baroreceptors, the frequency distribution curve became broad. Low curve of the figure showing that the pressure range increased 2.5-fold, frequently falling to as low as 50 millimeter mercury or rising to over 160 millimeter mercury. Thus, one can understand the extreme variability of pressure in the absence of arterial baroreceptor system. The importance of baroreceptor system is obvious to control blood pressure within narrow range. Are baroreceptors important in the long-term regulation of arterial pressure? No, I can say no. However, let's continue. The arterial baroreceptors provide powerful moment-to-moment control of arterial pressure, but their importance in the long-term blood pressure regulation is still uncertain because they tend to reset within 1 to 2 days to the blood pressure to which they are exposed. If, for example, the arterial pressure rises from normal value of 100 millimeter mercury to a high value of 160 millimeter mercury, in the beginning, very high rates of baroreceptor impulses are seen. However, the rate of baroreceptor firing returns to normal or nearly normal over a period of 1 to 2 days. Baroreceptors continuously send signals to the brain. Hey, blood pressure increase, do something. If the brain cannot decrease the blood pressure or does not do anything to decrease the blood pressure, then the baroreceptors say that, okay, whatever you do, I did my job. It is your responsibility later on. So it starts not to stimulate to the brain anymore. Okay. Now, actually, it is resetting the blood pressure to 160 millimeter mercury now. Over 160 millimeter mercury now, they start to fire again frequently. Okay, so this resetting of baroreceptors may attenuate their potency for correcting disturbances that tend to change arterial pressure for longer than a few days. Although experimental studies show that baroreceptors do not completely reset and therefore may contribute to long-term blood regulation by influencing sympathetic nerve activity of the kidneys. Okay, let me say a few words about this. So they decreases the sympathetic activity in the kidneys, so that what will happen in the kidneys, there will be vasodilation, and then this will increase glomerular filtration and vasodilation in the afferent arteriole. More blood will come to the glomerulus, and then glomerular filtration will be increased, and also tubular reabsorption will be decreased, so that urine formation will be increased, so that blood pressure will be decreased. Okay. All right. Now, cardiopulmonary reflexes help regulate arterial pressure. Located in the walls of both atria and pulmonary arteries are stretch receptors called cardiopulmonary receptors, or low pressure receptors, that are similar to the baroreceptor stretch receptors of the systemic arteries. These low pressure receptors play an important role in minimizing arterial pressure changes in response to blood volume changes. Okay, they are sensitive to the blood volume. Although low pressure receptors do not directly detect arterial pressure, they detect changes in pressure in the heart and pulmonary circulation caused by changes in volume, and they start reflexes that parallel to baroreceptor reflexes to make total reflex system more potent for controlling arterial pressure. Increased stretching of the atria causes reflex decreases in sympathetic activity to the kidney, which causes vasodilation of the afferent arterioles and increases the glomerular filtration rate, as well as decreasing the tubular reabsorption of sodium, so that these changes will cause the kidneys to excrete more sodium and water, in this way to get rid of the excess volume from the body. Now, control of arterial pressure by carotid and aortic chemoreceptors. These are chemoreceptors. These are not baroreceptors, but they still take part in the regulation of blood pressure. So they are sensitive to lack of oxygen, excess carbon dioxide, or hydrogen ions. Closely associated with the baroreceptor control system is a chemoreceptor reflex that operates in much the same way as the baroreceptor reflex, except that chemoreceptors, instead of stretch receptors, initiate the response. So they work in the low blood pressures. Chemoreceptors are located in the same locations in two carotid bodies, one of which lies in the bifurcation of each common carotid artery, and in several aortic bodies adjacent to the aorta. Whenever the arterial pressure falls below a critical level, chemoreceptors become stimulated because of diminished blood flow to the bodies and the resulting diminished availability of oxygen and excess buildup of carbon dioxide and hydrogen ions that are not removed by slow blood flow. Signals transmitted from the chemoreceptors into the vasomotor center excite the vasomotor center, which in turn elevates the arterial pressure. Now, central nervous system ischemic response. Central nervous system ischemic response increase the arterial pressure in response to decreased blood flow to the brain's vasomotor center. When blood flow to the vasomotor center in the lower brainstem becomes sufficiently decreased to cause cerebral ischemia, that is to say, nutritional deficiency in the brain, the neurons of the vasomotor center become strongly excited. When this occurs, the systemic arterial pressure often rises to a level as high as the heart can pump, which may be due to the effect of low blood flow, which causes buildup of carbon dioxide in the vasomotor centers. Increased carbon dioxide concentration is a potent agent stimulating the sympathetic nervous control areas of the medulla of the brain. Other factors, such as increased lactic acid, may also contribute to marked stimulation of the vasomotor center and increased arterial pressure. As I said, the brain is very selfish, especially in hypovolemic shock tables. When blood flow goes to very low values, brain sends signals to all blood vessels in the body via sympathetic nervous system, constricting signals and dilating its own blood vessels so that to keep alive, to stay alive, okay? This arterial pressure elevation in response to cerebral ischemia is known as the central nervous system ischemic response. This response is an emergency control system that acts rapidly and powerfully to prevent further decline in arterial pressure when blood flow to the brain becomes dangerously decreased. It is sometimes called the last-ditch, last-step mechanism for blood pressure control. On the left-hand side, you see fluctuations in the blood pressure due to ischemic response of the brain. When the brain receives enough blood, carbon dioxide will be removed, oxygen will be provided, so blood pressure returns to normal. But when it goes down, this time the blood pressure will not be sufficient to provide enough oxygen and to remove carbon dioxide and lactic acid, hydrogen, etc. And this will also stimulate again the blood pressure increase. So this is on the left-hand side, shows the ischemic response of the central nervous system fluctuations. On the right-hand side, you see the baroreceptor reflex oscillation. Now, Cushing reaction in the central nervous system ischemic response results from increased pressure in the cranial wall. We have a cerebrospinal fluid, as I said earlier. This fluid is made in the ventricles and circulates around the brain, keeping the brain from trauma of the cerebral bones, cranial bones, okay? Our brain is located inside of the cranium, and then this fluid behaves like a cushion, preventing damage in the brain. Sometimes, however, the pressure inside of the subcranial, subarachnoid area can go up, okay? When cerebrospinal fluid pressure rises to equal the arterial pressure, a central nervous system ischemic response will be initiated to rise the arterial pressure to as high as 250 mm mercury. This response helps protect the vital centers of the brain from loss of nutrition, which could occur if pressure in the cranial vault, cranial cavity exceeds the normal arterial pressure and compresses blood vessels supplying the brain. So this figure shows us this experiment What do we see here? There is a dark line here, and we have a catheter connected to the subarachnoidal space, so we can increase the pressure in the subarachnoidal space. When the pressure is increased in the cerebrospinal fluid in subarachnoidal space, as you see, blood pressure goes up. Here you can follow. Why? Because when you increase the pressure around the brain, it prevents the blood to reach the brain. So to provide oxygen and nutrients to the brain, blood pressure will be increased by ischemic response, and then very high. When you remove the pressure, when you decrease the pressure in the cerebrospinal fluid, then the blood pressure also goes down to provide enough oxygen, and nutrients to the brain. So, if cerebral ischemia becomes so severe that a maximal increase in arterial pressure still cannot relieve the ischemia, the neuronal cells begin to suffer metabolically, and within 3 to 10 minutes they become inactive, which causes the arterial pressure to decrease. So, after this lecture, now let's check if we have learned what we aim to. Are we able to describe the effects of sympathetic stimulation on blood vessels and heart? Yes. What is it? So sympathetic nervous stimulation constrict the blood vessels and increase the heart rate and contractility. So can we describe the effects of parasympathetic stimulation on cardiac function? Yes. Parasympathetic stimulation inhibits the cardiac function, slows down the heart rate, and then decreases the contractility of the heart. Can we define how the vasomotor centers of the brain control the sympathetic vasoconstrictor system? Yes. For example, when you are doing exercise, they stimulate the sympathetic vasoconstrictor system. They increase the heart function, they increase the blood redistribution, they increase vasoconstriction in the internal organs, and they cause vasodilation in the skeletal muscles, although local factors are also responsible for that. There may be receptor subtype differences in the skeletal muscles also. In coronary arteries, beta receptors are present, so epinephrine, the neurotransmitter of the sympathetic nervous system, causes vasodilation in the coronary arteries. So can you describe the sympathetic vasoconstrictor tone on blood vessels? Yes. Except capillaries, all blood vessels, arteries, arterioles, venues, and veins, they all receive sympathetic nerves, and then they are under sympathetic stimulation all the time. So this is called sympathetic tone. List of higher nervous system centers on the vasomotor system. Yes, you can list it if you want to. Define the effect of sympathetic stimulation on the adrenal medulla. Yes, we have talked about this. Adrenal medulla is connected to the sympathetic nervous system. When sympathetic nervous system is activated, adrenal medulla releases huge amount of epinephrine and norepinephrine to the blood circulation, increasing the heart rate, increasing the blood pressure, etc. Define the role of nervous system in the rapid control of arterial pressure. Yes. In the rapid control nervous system, in the long-term control, renal system is responsible. Renal system adjusts the blood volume, extracellular volume, and nervous system is controlling the sympathetic and vasomotor part of the autonomic nervous system, so that regulating blood pressure in the short term acutely. Okay. Explain the autonomic nervous system in blood pressure regulation during exercise. Yes, the heart contractibility and frequency of the heartbeat will be increased and then blood will be redistributed. So, can you describe how arterial baroreceptor reflex work to control blood pressure? Yes, we have carotid and aortic baroreceptors in our arcus aorta and carotid body, so they are sensitive to blood pressure, especially after 50 millimeter mercury. They start to fire when the blood pressure increases. So they decreases the fluctuations during daily activities, especially when you wake up. They thanks to their functions, our blood pressure does not fall to very low values, too low values, so that we don't faint. Can you define the importance of baroreceptors in the long-term regulation of arterial pressure? Yes, in the long term, baroreceptors are not effective because they adapt. Let's say blood pressure increases from 120 to 160 millimeter mercury, systolic pressure. In the beginning, baroreceptors will fire very, very fast, and then after a few days, they will stop firing. They will be reset to the new high blood pressure. Okay, so in the long term, their function is not that important as it is in the short term acute changes in the blood pressure. So baroreceptors are sensitive to blood pressure changes acutely, not chronically, we can say. So can you describe how cardiopulmonary reflexes help to regulate arterial pressure? Yes, there are stretch receptors sensitive to the volume, blood volume, and stretching of the atria, stretching of the pulmonary arteries. So if blood volume goes up or goes down, they also cause changes in the renal functions, especially when they are stretched. They cause vasodilation in the afferent arteriole. They decrease the sympathetic activity to the kidneys, increasing the urine output so that the volume of blood will go down and blood pressure will go down. Can you answer the question that whether carotid and aortic chemoreceptors take part in the arterial pressure control? Yes, although they are sensitive to chemical changes such as hypoxia, hypercapnia, and acidosis, they are also sensitive to blood pressure changes. They are sensitive to low blood pressure, however, compared with the baroreceptors, which are sensitive to high blood pressure. Can you define central nervous system ischemic response and Cushing reaction? Yes. If the brain is under pressure, for example, cerebrospinal fluid pressure can increase, preventing the blood flow into the brain. Brain cannot receive enough oxygen and cannot remove carbon dioxide and waste products. In this case, blood pressure will be stimulated. Also in hypovolemic conditions such as bleeding, the brain can cause strong contraction in blood vessels in other parts of the body, but vasodilation in the brain tissue itself to keep itself alive. So the brain is a selfish organ. It is the last thing that the brain can do before dies. Okay. Thank you for your attention.